Hello everyone, welcome. Today I'm going to start to work on a few examples about crystal structures. Well, let's suppose you have to find out how many atoms are present in, for example, FCC structure. FCC stands for face-centered cubic. It's essentially a simple cubic structure with 8 atoms sitting on the corners plus 6 atoms sitting on the faces of this cube. So to count the number of atoms in this unit cell, we need to think that we are dealing with the periodic structure, which is the case. And for periodic structures, we see that the atoms in the corners are shared by 8 unit cells. Conversely, the atoms on the faces are shared by 2 unit cells. Therefore, let's count the number of atoms here for this FCC structure. Would be something like 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms times 1/8, because each atom in the corner is shared with 8 unit cells, plus 6 times half, because each atom on the face are shared with 2 unit cells. Therefore, for a FCC unit cell, we have 4 atoms. We can think in a similar way for a BCC, which stands for body-centered cubic structure. It's essentially a simple cubic, but now with a single atom in the center of this cube. So if we apply the same concept here, there are 8 atoms in the corners times 1/8 plus 1. Note that the atom in the center is not shared with others unit cells. Therefore, the number of atoms in a BCC unit cell are 2 atoms. Examples of materials that crystallize in FCC structure are aluminum, gold, and nickel. And for BCC, the examples are sodium, iron, and tungsten. I used the simple cubic structure to break down the FCC and the BCC structures. And of course, for simple cubic, we have a single atom, right? We have here the simple cubic structure with only 8 atoms sitting on the corners, and 8 times 1/8, because each one of these atoms are shared with 8 unit cells. We have therefore 1 atom per unit cell in the case of the simple cubic structure. There's another crystal structure called diamond. I won't be able to draw it here for drawing limitations, but essentially the diamond structure is the sum of 2 FCC structures, where the second one is shifted with respect to the first one by 1/4. And if one FCC unit cell has 4 atoms, diamond structure that has 2 FCCs structures must have 8 atoms per unit cell, which means 4 atoms for each FCC. Materials that crystallize in a diamond structure are silicon, germanium, and carbon. So one might be interested in knowing how much of the unit cell is occupied by atoms. So to do this kind of calculation, we can define the atomic packing factor, or APF for short, and we make some assumptions such as atoms are hard spheres that are in contact with their nearest neighbors. I'll try to draw here what it means for let's start off with a simple cubic now. So before we go into details of the simple cubic structure, let's first define the atomic packing factor to be the volume of the atoms in the unit cell over the volume of the unit cell. So if we say that the edge of this cube is A, then the volume of our unit cell will be A to the power of 3. The volume of the atoms now, we have to find a way to relate the sphere radius of the atoms to the edge of the cube. Well, this is easy to do for this case. We have the radius here, r, another radius here, r. This is enough to establish the relationship between r and a. 2r equals to a, right? The volume of a sphere is given by 4 over 3 pi r to the power of 3. Here, if we solve for a, we have r is equal a over 2, right? And if we plug it to the volume expression, we have 4 over 3 pi a over 2 to the power of 3, and it gives us pi a over 3 over 6, right? And then the atomic packing factor for the simple cubic will be pi a 3 over 6 over a to the power 3. This cancels out this one. Then we have pi over 6, which is approximately 0.52, which is approximately 50%. So this result tells us that 52% of the unit cell is fulfilled with atoms. The other 48% is empty space. Well, we can do the same calculation for the FCC. So I'll draw it first so it will help us to visualize what's going on. So I don't know how helpful this drawing will be, but um, here we can see, let's suppose the same thing as before. The edge of our cube will be A. The main difference now is we have to consider the diagonal of our cube, of or at least of this um, square here, to determine the relationship between A and R. As you can see through this drawing, I hope it can convince you. We have R here, here we have 2R, and plus R again, right? And then we can just use the Pythagoras relation for the triangle here, which is R plus 2R plus R squared is equal to A squared plus A squared. Then we basically have 4R equals squared equals 2A squared. And we can solve for R and get R equals square root of 2 over 4A. So the volume of one atom, we can consider that an atom is a hard sphere, is going to be 4 over 3 pi r to the power of 3, and it gives us 8 square root of 2, 4 to the power of 3 times 3 pi a to the power of 3, right? And we can go even further and simplify it a little bit more to gives us pi a to the power of 3 to 4 times 3. It turns out that this is the volume for a single atom, but as we saw before, in a FCC structure there are 4 atoms per unit cell. Therefore we multiply this volume by 4, and we end up with the atoms, the volume of atoms prime. Just to differentiate the volumes, this now means all the atoms in this unit cell will be square root of 2 pi a to the power of 3 over 6. And then the atomic packing factor will be the volume of the atoms as before over the volume of the unit cell. It's gonna give us square root of 2 pi a to the power of 3 over 6 over a to the power of 3, right? Because the volume of our unit cell here is still the same. So this term cancels out this term here in the denominator, and we finally end up with square root of 2 pi over 6. It's approximately 0.74, 74%. Well, the 4 atoms in the unit cell of a FCC structure occupy 74% of its total volume. Likewise for the BCC structure, once again I'll draw here the structure in a 3D perspective to help us to visualize how to relate the radius with the cube edges. This is by far the worst drawing that I've made, but hopefully you can get the picture. Let me just draw here. I'll try to relate the radius with the edges once again. As before, if we take this diagonal here from point A to point B, so A to B, we have 4 R's, 2 for the atom in the middle, 1 for each 1/8 of the atoms on the corners, and this distance from B to C here, B to C is A, and now we are come to B to A. It's the diagonal of the face at the bottom. It's basically square root of 2a, right? And if we write the Pythagoras relation here, a b squared bc squared plus ba squared, we end up with 16r squared plus a squared plus 2a squared, 16r squared, 3a squared. If we solve for r, we have over 4a, right? Therefore, the volume of one atom here will be 4 over 3 pi a, sorry, r to the power of 3. But r is square root of 3 over 4, and then 3 pi square root of 3 over 4a to the power of 3. Well, to make the long story short, for one atom we have pi square root of 3 4 squared a squared, but we have for a BCC structure we have 2 atoms as we solved before, then we gotta multiply this per 2, and then we end up with pi square root of 3 a squared over 8 to the power of 3, sorry, over 8, and the atomic packing factor will be this term cancels this, just as before, 68, oh sorry, it's gonna give us 0.68, approximately 68%. As an exercise, find the relationship between R and A for the diamond lattice, as well as its atomic packing factor. So I'll tell you the answer here. the relationship between R and A is 8R equals a square root of 3, and the atomic packing factor is 4/64 pi square root of 3, which comes to approximately 0.34%. So I said before that silicon crystallizes in the diamond lattice. If the lattice constant of silicon is 5.43 angstroms, what would be the distance from the center of one silicon atom to the center of its nearest neighbor? So this is a trivial question. We just need to think that the nearest neighbors are two silicon atoms that are in contact with each other. In other words, we have one silicon atom here and another silicon atom here. So they are the nearest neighbors, and the distance from center to center is basically 2r. So if we solve for r in this expression, we have r equals to a square root of 3 over 8, then 5.43 square root of 3 over 8. It gives us 1.176 angstroms, and the distance, the 4, will be the distance between the distance center to center between two nearest neighbors will be 2r. 2 times 1.176, it comes to 2.35 angstroms. So this is the distance between two nearest neighbors in the diamond lattice in the silicon structure. We can also calculate the number density of silicon atoms in the unit cell, which is the number per centimeter cubed. So basically, in a unit cell, the number of atoms, the silicon atoms in a unit cell is 8 atoms, right? Remember, a diamond is a FCC, 2 FCC together, and we have 4 atoms per FCC, coming to a total of 8 atoms. And the volume of the unit cell is a to the power of 3, and it will be 5.43 angstroms cubed. We can, if we do this calculation and transform to centimeter cubed, it will give us 1.6 times 10 to the power of minus 22 centimeters cubed. Therefore, the number density will be 8 over this tiny number here. Gives us approximately 5 times to the power of 22 centimeter minus 3. Finally, we can calculate, for example, the mass density of silicon. The unit here, grams per centimeter cubed. We can use the formula that the number of atoms is equals to the Avogadro number times the mass density times the volume over the molar weight. We can solve for the mass density, and it's gonna give us the number of atoms times the molar weight over the Avogadro number times V, and here we identify this number of atoms per volume, exactly the number that we calculated before, and then it's 5.2 times 28.09. This is the molar weight of silicon over 6.02223. This is the Avogadro number. Then the mass density will be approximately 2.33 grams per centimeter cubed. So as you can see, by very simple assumptions, we can find very useful informations. Like, for example, the value of silicon density of 2.33 grams per centimeter cubed is very close to the value found in the literature. So what if instead of having silicon, we consider gallium arsenide? What is the number density? So before we answer this question, let's see what gallium arsenide is. Gallium arsenide is a 3,5 compound. What does it mean? It means that it is a compound made of elements listed in the columns 3 and 5 of the periodic table. So the gallium arsenide also crystallizes in the diamond lattice. We give it a special name for the case of the gallium arsenide. We call it zinc blende structure, which is basically still a sum of two FCC lattices, FCC1 and FCC2, where the gallium occupy the first FCC, meaning 4 gallium atoms occupying the first FCC, and 4 arsenic atoms occupying the FCC2. Also, the second FCC is shifted with respect to the first FCC by 1/4, as before, because this is a diamond lattice. We just give it a new name. Alright, if the gallium arsenide, the constant lattice for the gallium arsenide is 5.65 angstroms, what is the number density? Well, there are two number densities involved, one for the gallium and the other for the arsenic. We can calculate the number density for the gallium and the number density for the arsenic. But not that. For both FCC, the unit cell, the diamond unit cell, has two FCC structures where each one of them is occupied by gallium, 4 atoms, and the 4 atoms of arsenic in the other FCC. And both FCC composes the unit cell. So we expected that the number density of these atoms to be equal, right? Because the volume of the unit cell is also the same for both. Well, we can use the lattice constant to calculate the volume of the unit cell. It's simply 5.65 angstroms to the power of 3. If we convert it to centimeter cubed, it will be 1.80 to the power of minus 22 centimeter cubed. And then the number density, I'll call it simply number density because I'm referring to both atoms, gallium and arsenic, will be 4 over the volume of the unit cell, which is 1.80 10 to the power of minus 22. It will give us approximately 2.22 times 10 to the power of 22 centimeter minus 3. So another popular semiconductor is called germanium, and the germanium also has a constant lattice of 5.65 angstroms, and also crystallize in the diamond lattice. We can therefore calculate the number density for germanium. I'll do it directly. I'll just give you some arguments to convince you that what I'm about to affirm here. Germanium crystallizes in the diamond structure. The diamond structure has 2 FCC lattice or structures. Therefore, we have 8 atoms in total, 8 germanium atoms in total over the same volume that we used for gallium arsenide. Therefore, here we expect to find the double, twice the value of the number density of each individual gallium and arsenic, which is 4.44 times 22 centimeter minus 3. Good. Let's have a look into another example. Suppose a material is composed of 2 types of atoms. Let's say atom A and atom B, where atom A has a radius Ra of 2.2 angstroms and Rb 1.8 angstroms. Also, let's assume that this material crystallizes in a BCC structure. To recall, the BCC structure is simply a simple cubic structure. And one might ask, what is the lattice constant of this material? I mean, of the unit cell of this material. Well, we can use the same approach used before. we can take this diagonal here, and we have 3 atoms along of this diagonal, meaning our total distance will be, the diagonal of the cube is square root of 3a. It must be equal to RA plus 2RB plus RA. So what I'm assuming here is the atom A occupies the corner. Here's the atom A, the corners, and the atom B is in the center, right? This here is the atom B. All right, so if we perform this calculation here, we comes to 2RA plus 2RB square root of 3A, and to make the long story short, A will be equal to 2 over square root of 3 RA plus RB, which is approximately 4.62 angstroms. We can calculate now the number density for the atom A and B, and as we saw before, for a BCC lattice, the unit cell has 2 atoms in total. As our unit cell has atom A and atom B, we have 1 atom A and 1 atom B, right? Therefore, the number density of A is equals to the number density of the atom B, which is 1 over, I'll do it directly here in a centimeter cube, 4.62 times 10 to the power of minus 8 to the cube. It's approximately 1.01 times to the power 22 centimeter minus 3. What if we exchange the position of atom A and atom B? The situation now is atom B is in the corners of our simple cubic structure, and the atom A are in the center of our cube. Well, so the relationship between A, the lattice constant, and the radius RA and RB is still the same as we found for the previous case. A will be 4.62 angstroms. If we calculate the number density for A and B, you can compare this structure with this structure. The number of atoms is still the same, and therefore the number density will be the same, found right here. So we're gonna get the same results. The conclusion of that is we're dealing with the same material. Doesn't matter if A is in the corner or B, the material is the same. It might sound strange. I changed the position of the atoms A with B, and the material is still the same. Yes, and the answer for that is we're dealing with the periodic structure. let me try draw it down here to help you understand the concept of periodicity and why periodicity implicates in this kind of pseudo-strange result. This drawing is similar to this drawing up here, where white atoms occupy the corners and the yellow atoms occupy the centers. However, if we look carefully at this yellow cube inside this array of white cubes, the yellow atoms for this cube occupy the corner of the yellow cube. And this particular atom here, which is a white atom that occupy a corner of the white cubes, now it occupies the center of the yellow cube. What you can see from this is the periodicity implies in doesn't matter if you exchange the position of atom, you're basically change the perspective you're looking at. The thing, the properties, everything remains the same. So now let's see a few examples on Miller indices. As we're dealing mainly with the crystalline semiconductors, one might ask how to specify planes and directions in crystal structures. Well, Miller indices are used for that purpose. This part is to illustrate what Miller indices are all about. So it has a very simple description, and to illustrate that, let's draw here a plane. Let's see how it looks like. X, Y, and Z axis, and let's draw one plane here. There are three intercepts, one on the x-axis, another in the y-axis, and the third one here on the z-axis. Let's put here some random numbers like 2a, a, and 2a. Well, the first step, this is the plane. The first step of the description to determine the Miller indices is to write down the intercepts, XYZ axis intercepts. For our example, the intercepts are 2a, a, and 2a again. That's for x, y, and z. There is no need to carry the a around. We understand everything is measured in units of a. We can simply write 2, 1, 2. The second step of our description is to invert those intercepts. Then 2 becomes half, 1 is simply 1, and 2 becomes half. And the third step is to rationalize those numbers. We can simply multiply by 2, then there is 2, sorry, not 2, 1, 2, and 1. So these are the Miller indices for the plane sketched right here. we can simply write the Miller indices for this plane as 1, 2, 1 again, between parentheses. There is a name for each one of these numbers. The first index we call H, the second K, the third L. The Miller indices in general are H, K, L. Now let's see a few more examples, including determine the Miller indices from the plane, as well as drawing the plane from the Miller indices. Now, taking our description, the first step is to write down the intercepts. There is no intersection for the x-axis. Then we write infinite. For the y is a, and for the z is also a. We can drop the a's. It comes to infinite, 1, 1. The second step is to invert those. 1 over infinite, we can take here for simplicity as 0, and remains 1 and 1. The third step, rationalize these three numbers, which will keep them as 0, 1, 1. Therefore, the Miller indices for this plane are 0, 1, 1. We can also have another example, like so for this plane, the first step, the intercepts are a, minus a, and 2a. We can simply drop the a's, 1 minus 1 and 2. We can now invert those, 1 minus 1 and half, and rationalize it. It comes to 2 minus 2 and 1. Therefore, the Miller indices for this plane are 2 minus 2 and 1. So what if we have the Miller indices instead of the plane? For example, 0, 1, 0. Oh, by the way, we don't need to use command to separate the Miller indices HKL. We can drop them out. From now on, I write it as it's shown here. So for this particular case, it's easy to see that the plane, based on our description, will simply be this plane right here. Moving on to a more difficult example, 2, 0, 3. We can think in our description in the reverse mode. So this is our step 3. How the step 2 should look like in order to get this step 3? It should look like something like 1 over 3, 0, and 1 over 2. In such a way that if I multiply the step 2 by 6, I will end up with this Miller indices up here. And based on this step 2, how the step 1 should look like? Well, the step 1, thinking in a reverse mode, in our description, the step 1 should look like 3. To find 0 in the second step, the first step, this Miller index should be infinite, and here should be 2. So now these are the intercepts, and we're able to draw the plane. X, Y, Z, where X is 3A and Z 2A, and no intersection on the y-axis. So this is all for this tutorial, everyone. Thanks for watching. I'll see you next time. Bye bye.